In this session, let us see a detailed explanation of intrinsic semiconductor. So, intrinsic semiconductor, we know that semiconductor, there are two types of semiconductor. One is intrinsic and another is extrinsic. So, extrinsic has P type and N type, and intrinsic, the other name of intrinsic is pure semiconductor. So far, in first unit in conducting materials in physics, engineering physics 1, we have come across so many charge carriers, but that purely represents only electrons because conductors have majority electrons. But here in semiconductors, along with electrons, holes also will play a role. So here in intrinsic semiconductor, the number of holes, the number of electrons will be equal to number of holes. So now we are going to derive an expression for the number of electrons in conduction band. So number of electrons in conduction band, number of holes in valence band, and their total carrier concentration. So their total concentration. So we are going to see 3 topics at a time. So first we can see the number of electrons in conduction band. So number of electrons in conduction band. So for this we can see the diagram. So these are the energy bands. So there are so many energy bands here, and let us start with minus infinity and ends with plus infinity. We know that the bottommost band is valence band and the topmost is conduction band. So the bottommost band is valence band, and this is a maximum level of the valence band named as EV. And then the topmost band is conduction band. So it starts with EC. This is the starting point of the conduction band is EC, and the ending point is plus infinity. So here the starting point is minus infinity and the ending point is EV. So in intrinsic semiconductor, since the number of electrons and holes will be equal, the Fermi level will be exactly present at the midpoint of this. So between EC and EV, at exactly the midpoint, the Fermi energy level will be present. We know that the Fermi energy level is a maximum level up to which the energy levels are filled with electrons. So here our task is to prove that EV is equal to EC plus EV by 2. So you want to prove this because we want to prove that this is exactly at the midpoint of EC and EV. So for that, you have to go for the expression. So number of electrons in conduction band will be the starting one. So we know that the dN can be written as the combination of density of states and Fermi distribution function. That is, if you want to find out the number of electrons in conduction band or holes in valence band, then you have to product the density of states and the Fermi distribution function. So density of states into Fermi distribution function. So here, so dN can be written as density of state is given as Z of E into dE into Fermi distribution function 1 by 1 plus e to the power of E minus EF by KT. That is Boltzmann constant. Either this K can be written as capital K to the suffix B or even as small k. So now we are going to substitute the corresponding expressions for this. So dN is equal to density of states. In the previous session we have seen the expression for that, 4 pi by h cube into 2m to the power 3 by 2 e to the power of half into dE. So this is the expression for density of states, and the Fermi distribution function is as such. So 1 by 1 plus e to the power of E minus EF by kT. Okay. So this will be the general expression. Now we want to see how this expression turns according to our topic, number of electrons in conduction band. So we can derive this in a simple manner. So first the simplification. So what are the simplification steps to be followed? Number one, you want to integrate both the sides. So first integrating both these sides. So integrating both the sides, that is introducing the integral symbol on both the sides. The second one, the limit, because if integration exists, then the limit is the most needed one. So what can be the limit for that? Now you are concentrating the number of electrons in conduction band. So you are concentrating only this portion. Since we are concentrating this portion, the beginning limit will be of EC and the ending limit will be of plus infinity. So the integral EC to plus infinity. So this will be the limit here. The third one, the third simplification is, so you have done a simplification by introducing the integral and then substituting the limits. Next coming here, because h is a constant, Planck's constant, so it's a constant, nothing can be done in it, and m, the mass can be changed as effective mass. So m is changed as effective mass m star. And the fourth simplification is the energy level E. Even though there are so many energy levels, you are concentrating only the energy levels which are present in the conduction band. No need of all these energy levels below this conduction band. So they can be neglected. So the ordinary, this energy level E can be written as the entire energy level minus of this portion. Suppose if the value is 120, the number of energy level, the value is 120 and this is of 90, how can you find out the remaining value? 120 minus 90, 30. So 30 will be the remaining portion. So you want to concentrate like this. So you can write the ordinary E as E minus EC. And the last substitution, not substitution, simplification. So you have done an introduce an integral, substitute the limit, and the m is changed as m star, and the ordinary energy is changed as E minus EC. And the next simplification is done in Fermi energy level. Now in this Fermi energy level, see this EF, where does this lie? This EF is below the energy levels of the conduction band. So they have a very less value. So when this is less, the entire result will result in negative. So it will be of negative. So if exponential of that will be of in negative. But see this energy value is nothing but one of the energy levels in conduction band. So if this is in positive, the exponential of that value will be more effective than this numerical value 1. So since e to the power of E minus EF by kT is greater, very much greater than the first term 1. So it will be having a huge value because exponential of this positive will be having a huge value, and that value will be much more greater than this numerical value 1. So since it is greater than 1, the first term can be neglected. So first term can be neglected. So what is the first term here? Just 1. So this 1 can be neglected. So this becomes as 1 by e to the power of E minus EF by kT. So for simplification, I can bring this to the numerator. So e to the power of minus E minus EF by kT. So this can be written as e to the power of EF minus E by KT. So now I can substitute all the simplifications in this equation. So let us number this equation as 1. So the 5 simplifications are there. So I can substitute all the 5 simplification steps in this equation number 1, so that you will be able to finish this. So dn is equal to, now first integrating both sides. So take the integral. So integral 4 pi by h cube, and the limit also, the integral limit is from EC to plus infinity. And the next, the ordinary m changes up as m star. So here, since we are concentrating electrons in conduction band, the similar mass will be of for holes in valence band. So in order to differentiate that, we can have the suffix as E here. If it is of electrons, it is of E. Holes means it will be of H. Now this E becomes as E minus EC to the power half into dE into E to the power of EF minus E by KT. So we have written the expression for density of states and then Fermi distribution function, and we have taken so many simplifications. So no need to show the simplification step by step. So let us calculate all the simplifications at a time, and then you can substitute everything in a single step. So when you integrate this left side, it becomes as n, which means the number of electrons. So here, before integrating this, you have to remove all the constant terms because they cannot be integrated. So what are the constant terms here? 4 pi by h cube. So this can be taken outside, and 2 m e star to the power 3 by 2. So this can be taken outside, and the remaining here e to the power of EF. Fermi energy level is also constant in intrinsic semiconductor. They are exactly at the mid portion of conduction and valence band. So they are also constant, and that cannot be integrated. So take it out. So e to the power of EF by KT is taken outside. So now what are the leftover portions? So EC to plus infinity. So the leftover terms are E minus EC. So E minus EC to the power half into dE so E minus EC to the power half into dE, and here e to the power of minus E by KT. So now integrating this is a bit complex. So you have to consider, you have to simplify this by considering this term as x. So let E minus EC is equal to x. Let this term be equal to x. Now what will be of E? E can be taken as x plus EC. So instead of this, you can substitute x, and instead of this E, you can substitute x plus EC. Now what can be substituted for dE? So now in order to substitute for dE, you are differentiating this. So dE becomes as dx, and this becomes as 0 because it's constant. The conduction band level is constant, valence band level is constant, and EF is also constant. So you cannot differentiate this. This becomes as 0. So the leftover will be of dE is equal to dx. Now by substituting everything there, you will be able to arrive at the solution. But before that, you want to replace the limits also. So when the energy level is EC, because this EC is one of the energy level, plus infinity is another energy level. So when the energy level is EC, what can be the x? Or what can be the x? So EC minus EC is equal to x. So So when you substitute this E as EC, X will become as 0. Similarly, when you substitute the energy level as plus infinity, X becomes as plus infinity itself, because anything with this infinity will be of plus infinity, will be of plus infinity only. So by substituting all this in the above expression, we will be able to arrive the solution. So n is equal to 4 pi by h cube 2m e star to the power 3 by 2 e to the power of ef by kt. So you have written everything. Now the substitution starts. Integration, the limit changes as EC becomes as 0 and plus infinity will be retained the same thing. So from 0 to plus infinity. Now this becomes as x to the power half, and this dE becomes as dx. So let us have that at the end of the expression. So e to the power of this e will become as x plus ec. So minus x plus ec by kt. It's kt. So now before integrating this, one more constant has been locked inside. That is nothing but ec by kt. You have to take that outside. So when you compare that term with the terms outside, I think we can link this with this, because this also has a by kt and this is also of divided by kt. So n is equal to 4 pi by h cube 2m star to the power 3 by 2 e to the power of ef. Now I can take this outside, minus ec by kt. So minus ec by kt, and the integration 0 to plus infinity x to the power of half, and the leftover portion here will be of just e to the power of minus x by kt into dx. So now I will just recall this. So this was the expression we got for substituting the number of density of states and Fermi distribution function and applying all the simplifications. So by substituting all this assumption, that is assumption concept here, you are able to arrive this expression. Now this can be easily simplified. No need to integrate in detailed one. Already it has been integrated by using gamma function. So using gamma function, we can have the answer for this, e to the power of x to the power of half e to the power of minus x by kt into dx can be written as kt to the power 3 by 2 pi to the power of half by 2. So now by substituting that, so n is nothing but 4 pi by h cube 2me star to the power 3 by 2 e to the power of ef minus ec by kt and kt to the power 3 by 2 pi to the power of half by 2. So by substituting gamma function, we can simplify this. So this 2 and 4, it goes off. So now I think I can club all the terms which has a power of 3 by 2. So n is nothing but 2m e star. So 2m e star is coming under 3 by 2. Kt is also there, kt. Now this pi is nothing but pi to the power of 1. and here the pi to the power of half. So I think I can club this. So this pi to the power of 1 and pi to the power of half, I can club this and I can take here. So that also comes under the power 3 by 2. Now h cube. So h cube, when it is written within 3 by 2, it becomes as h square. So when it becomes as h square, when it is written like this. So the h square also can be taken inside the power 3 by 2. And this 2 is left over. So this 2 can be front. Now write the remaining terms, e to the power of EF minus EC by KT. So this will be the expression for number of electrons in conduction band. Similarly, we have to see the expression for number of holes in valence band. The only changeable terms are ME becomes as MH star, and this EF minus EC will become as EV minus EF. So you have to bring this. So let us see. So this will be the entire expression for the density of electrons in conduction band. So next we can see the density of holes in valence band. So the next title is number of holes in valence band, or it can be also said as density of holes in valence band. So the same diagram, no need to draw the diagram you people, but for our understanding I am drawing it once again. So this is of minus infinity to plus infinity, and the bottom band will be of valence band, and this will be the end of the valence band, and this is the beginning of the conduction band, and the end, the limit is plus infinity, and these are the energy levels, various energy levels, and EF will be exactly present at the midpoint. So in the last few minutes, we have seen the expression for this conduction band, electrons in conduction band. If all the electrons goes from valence band to the conduction band, the empty sites will be called as holes. So you want to, we know that in intrinsic, the number of electrons will be equal to number of holes. But even though you want to produce an expression for that, so you are going to see the holes in valence band, you are going to concentrate only in this portion. We don't want the above portion, we need only this portion. So here dP. So the number of holes are represented as dP is equal to density of states. Density of states into Fermi distribution function purely talks about the presence of electrons. But here we are going to talk about the presence of holes. So instead of having as F of E always used to be denoted for electrons. So here, since the holes plays a role, we are going to take 1 minus F of E. So 1 minus F of E will be used to denote the holes. Now writing the expression for that, Z of E dE. So 4 pi by h cube 2m to the power 3 by 2 e to the power of half into dE into 1 minus F of E. So 1 minus 1 by 1 plus e to the power of E minus EF by KT. Okay. So similarly, whatever we have done for the electrons in conduction band, the same simplifications we'll be seeing for the holes in valence band. So what are the simplifications? Number 1, integrating both the sides. So taking integral on both sides. The next one is giving the limit for the integral. So what can be the limit for the integral? Since we are going to concentrate at the bottom band, the starting limit will be of minus infinity and the ending limit will be of EV. So, minus infinity to EV. So, this will be the limit for the integration. The third simplification, the m will be rechanged as m star. So, m will be changed as me star. The fourth one, this E. For in conduction band, this E was replaced as E minus EC. Since we are going from negative, lesser to the lower, higher one, the E in this holes in valence band should be replaced by EV minus E. So, this E will be replaced as EV minus E. And the fifth one is, if you see in each and every notation we have made the simplifications. The last simplification will be done here. But before this, you can simplify this and have. So, let us take LCM for this. So, 1 plus E minus EF by KT. So, when you take the LCM, 1 plus e to the power of E minus EF by KT minus 1. So, minus and plus goes off. So, the leftover term will be of E minus EF by KT divided by 1 plus e to the power of E minus EF by KT. Now, only in this term you have to make the simplification. So, what simplification can be done? Where is this EF present? EF is present above EV. So, this EF is present in the energy levels, any one of the energy levels in EV. So, EF is just above EV. So, the value will be very huge. So, this value will be very huge, sorry, this value will be very, very less because it will be of negative. So, this EF is above EV and this will be a dominant one. So, it has a negative value and exponential of that negative value will be it has a very, very lesser value than the numerical value 1. So, since this EF is greater than, EF is greater than E to the power of E minus EF by KT is lesser than 1. So, by neglecting the second term, so here in number of electrons in conduction band, the first term was neglected. In number of holes in valence band, the second term will be neglected. So, now by applying all this in this equation, so you can apply all the simplifications here. So, integral, you are introducing the integral on both the sides and the limits will be of minus infinity to EV 4 pi by h cube and 2m. So, this m can be replaced as m star. In order to differentiate, you are introducing a suffix h to the power 3 by 2 and e to the power of half is replaced as EV minus E. EV minus E to the power of half into dE into the Fermi distribution function. So, the second term, this term can be neglected. So, only the numerator alone will be existing, E minus EF by KT. So, this is a final simplification substituted there. Now, you can integrate this. So, by integrating the left side, you will be able to get P, which denotes the number of holes in VB. So, before integrating this, you have to take all the constants outside, what we did in electrons and conduction band. So, 4 pi by h cube, 2m h star to the power 3 by 2 and e to the power of minus EF by KT can be taken outside. So, all these are constants, e to the power of minus EF by KT. So, then the integration starts minus infinity to EV minus E to the power of half and the leftover term will be e to the power of E by kT into dE. So by substituting all the simplifications, we arrive at an entire expression like this. So now, as we consider the electrons in Cb, we have to consider here this as x. So let x is equal to EV minus E. So now what can be E? So bring this side. So minus E is equal to minus E, or even you can have like this. E can be taken as x minus EV. EV minus x or anything else, no problem. So now by differentiating this becomes as 0 and this becomes as minus dx. Similarly, when you substitute the integral, when the energy level is minus infinity, what can be this? What can be the x? Minus of minus infinity. So when E is minus infinity, this becomes as plus. So anything to the plus infinity will be of plus infinity. So minus infinity becomes as plus infinity. And when the energy level is EV, what will be x? So x is equal to EV minus EV, that is equal to 0, because when the energy level is substituted as minus infinity, you are able to get plus infinity. When the energy level is substituted by the upper limit EV, the x becomes as 0. So now you can apply everything here. So P is equal to 4 pi by h cube 2m h star to the power 3 by 2 e to the power of minus EF by kT, and the integral minus infinity changes as plus infinity and EV changes as 0. And this can be written as x to the power of half and e to the power of E. E is nothing but EV minus x. So EV minus x by kT, and this dE is nothing but minus dx. So in order to remove this minus sign, polarity, you can just interchange the limits of this. So P is equal to 4 pi by h cube 2m h star to the power 3 by 2 e to the power of minus EF by kT, and the limit is changed as from 0 to plus infinity x to the power of half e to the power of EV minus x by kT into dx. So now before integrating this, once again you have to take the constant outside. So here the constant is EV by kT, and you can club with this. So P is equal to 4 pi by h cube 2m h star to the power 3 by 2 and e to the power of EV minus EF by kT. So 0 to plus infinity x to the power of half e to the power of, the leftover is nothing but minus kT into dx. And similarly, whatever we have done in electrons and Cb, we can do this for holes in Bb also. So by using the gamma function, the integration of 0 to plus infinity x to the power of half e to the power of minus x by kT into dx is simply, you can write this as kT to the power 3 by 2 pi to the power of half by 2. So now by substituting and simplifying this, 4 pi by h cube 2m h star to the power 3 by 2 e to the power of EV minus EF by KT, and writing this gamma function pi to the power of half by 2. So by simplifying this, the 2 and 4 goes off, and this pi to the power of 1 can be clubbed with this pi to the power of half. So similarly, you can take all the terms which comes under 3 by 2. So 2 pi mh star kt by h square to the power 3 by 2 e to the power of EV minus EF by KT. So this will be the entire expression for the number of holes in valence band. So I think you can understand this, and we have seen the differences of number of electrons in conduction band. The same thing, only a small change. So e to the power of EC minus EF by KT. So this becomes as EF minus EC. So EF minus EC, and here this is of EV minus EF, MH star, and this is of ME star. So these are the two differences between the number of holes in valence band and number of electrons in the conduction band. So now we can see the third one, the intrinsic semiconductor, by clubbing both. So what can be the total carrier concentration in this semiconducting? So you can see the intrinsic carrier concentration. So the number of holes and electrons, you have found out the expression separately for electrons and separately for holes. Now putting together, you will be able to find out the entire expression for the carrier concentration. So in intrinsic, the pure semiconductor, we know that number of electrons is equal to number of holes. Number of electrons is equal to number of holes, that is nothing but N is equal to P. So this was the expression derived for the electrons in conduction band, and this was the expression derived for the holes in valence band. So in pure semiconductor, both are equal. Now we have to substitute the expression for both, and we have to simplify this. So what was expression found for that? 4 pi by h cube 2m e star to the power 3 by 2 e to the power of E minus EC by KT. So this was the expression for N. And now you want to substitute for this, 2 into 2 pi me star KT by h cube to the power 3 by 2. So similarly here, 2 into 2 pi mh star KT by h square to the power 3 by 2 e to the power of EV minus EF by KT. So this was a expression found for both, and you can simplify this. So except this one term in both the sides, all the other terms can be cancelled. So the 2 gets cancelled, 2 pi KT by h cube, everything gets cancelled instead of this term. ME star to the power 3 by 2 and e to the power of EF minus EC by KT is equal to MH star to the power 3 by 2 and e to the power of EV minus EF by KT. So everything gets cancelled. Now you bring all the m stars to one side and exponentials to the opposite side. So minus Kc by Kt by e to the power of EV minus EF by KT is equal to MH star by ME star to the power 3 by 2. So like this. Now you can take log on both sides, or before that you can bring the denominator to the numerator. So e to the power of EF minus EC, when this is brought to the numerator, minus EV plus EF by KT is equal to MH star by M E star to the power 3 by 2. So e to the power of 2EF minus is taken as a common thing. So EC plus EV by KT is equal to mH star by m E star to the power 3 by 2. So now taking log on both sides. So taking log on both sides. When you take log, the log and the exponential gets cancelled, and this becomes as 2EF minus EC plus EV by KT, and this becomes as log of mH star (3 by 2). Now we can cross multiply this. So 2EF minus EC plus EV is equal to, so before that you can bring this, so KT plus, sorry, log of mH star by me star to the power 3 by 2. So now I need only EF alone on this side. So taking bringing all the other terms to the opposite side. So 2EF is equal to EC plus EV plus KT into log of mH star by me star to the power 3 by 2. So now EF can be written as EC plus EV by 2 plus KT by 2 into log of mH star by me star to the power 3 by 2. So now our task, I think you have remembered the first task what we see in the beginning of this topic was we have to bring EF is equal to EC plus EV by 2. I think we are approaching that. So by chance, if because the effective mass of the hole and the electrons are more or less they have the same value. So mH star is approximately equal to me star, then that gets cancelled. So the same thing will be existing, mH star and me star. So this gets cancelled, this becomes as 1, and log 1 is nothing but 0. So log 1 can be taken as 0 because this mH star by mH star both are same. So when you substitute either the h by e or e by h, this gets cancelled and becomes as 1, and log 1 becomes 0, and finally, so 0 into KT by 2 is 0. So finally you have arrived the expression as EF is equal to EC plus EV by 2. So this is nothing but the information about the intrinsic carrier concentration, and you have shown this, you have verified this. So this is EV and this is EC. So in this energy band diagram, the EF is exactly at the EF is exactly at the band gap. So EF can be written as EC plus EV by 2, and through the derivation separately, that is number of electrons in conduction band, number of holes in valence band, you have found out separately, and then by putting together you have found the expression for the intrinsic carrier concentration, and from that you have found that EC is equal to EF is equal to EC plus EV by 2. Okay, thank you.